So hi everyone, I'm Andrea Gaspari. I'm a PhD student in Loma in Bordeaux. And today I will present the work I've been doing under the supervision of Fabio Pistolesi and Rémi Avrier. And it's actually in collaboration with Florian Marquardt. As you may read, the title is, the goal is to do neuromorphic computing with optomechanical oscillator. And so normally I will give a brief introduction about neuromorphic computing, but I think you are all well familiar. So we'll get straight to the point, which is optomechanics suitable for neuromorphic computing, and can optomechanics provide a valid physical neuron? So to address this question, I would like first to provide you a bit of an overview about the fundamentals of optomechanics, and eventually give you our results about what we've been able to do with optomechanical networks. So let's start with the fundamentals. So the easiest way to picture optomechanical system is that of a Fabry-Perot cavity, in which in fact we have a cavity, which is normally parameterized by the resonance frequency omega c and the cavity decay rate. But the feature is that one of the two mirrors is placed on a movable plate. So this creates a natural coupling between the cavity population and the mechanical degree of freedom. And on top of that, we also have a laser input. This will allow us to control a bit the whole system. To describe this system, you usually use an Hamiltonian of this kind, in which you can see that essentially is it's two harmonic oscillator, one for the cavity and one for the mechanical degree of freedom, and an interaction term, which is essentially the coupling between the position of the mirror and the cavity population. So allow me now to fast forward a little, and I will consider the semi-classical limit. So essentially, for large population of the cavity population and the mechanical degree of freedom, so I consider the coherent amplitude of the two variables. I will put myself in a rotating frame, and I will consider dissipation sources, but not noise at this point. So the equation of motion that I get is something like this, where the new variable appearing are the detuning and the pull parameter. So let me comment a bit on this equation. I decided to derive this equation because I think that now it's pretty clear how the nonlinearity arise. The system is intrinsically nonlinear. You can see it from here and from here, actually. And essentially, for the mechanical system, we have a damped harmonic oscillator with the effect of radiation pressure force. This actually, it's a very rich model, and in particular, by controlling the power input from the laser and the detuning, we are actually able to pump energy or remove energy from the system. This is actually to a very rich dynamics. We can cool the system, heat the system, reach bistable, multi-stable dynamics, chaotic dynamics, and so on and so forth. And this is to say that actually optomechanics is a very populated field. There are a large number of implementation. And here I just wanted to report some of the range, of the operational range that you can achieve in optomechanics. But more importantly, I'm actually interested in the blue detune regime, which we can achieve when the detuning is positive, because in this regime, you can actually pump energy in the system. And so actually now I benefit from the previous talk. Ideally, by pumping energy, we'll at some point reach a critical point in which essentially the energy we're pumping is higher than the energy the system is losing. And so we enter a so-called self-sustained oscillation regime. This for us was very interesting because it's actually based on this that we eventually designed our optomechanical network. And eventually, the idea is that once we are in this regime, we can switch variables and we can use an amplitude phase description. And as I will see later, I will especially focus on the phase because it's actually an independent variable in the sense that it has no reference to the lab, let's say. And to describe this model and eventually the self-sustained oscillation close to the limit cycle, we actually get those two equations. This is a work done in this paper, but okay, well, never mind. The important things to retain here is that those two elements, well, actually it's one, will be the building block for our optomechanical network. So from here, I will now show how to build an optomechanical network, at least in our idea. So the idea is that now what we need is coupling. So to do so, our first thought was actually to use drum resonator, and again, I can benefit from the talk from before. Why that? Well, the main idea is that those type of implementation can be coupled capacitively, which for us was very convenient. And on top of that, we especially specialize in syndrome resonator because we wanted to actually check some of the operational, the working range. And in particular, for those drum resonator, we verified that they do exhibit self-sustained oscillation in the nanowatt regime, so using a nanowatt pumping. And eventually, they also, we can work with that in the sense they are on the micrometer size, which seemed quite convenient for us. And with those, so as I was saying, we design a way to couple them capacitively. And okay, when you have two, it's pretty simple. You just put them one on top of the other. When you start having more, actually, you can think of two topologies to couple them, what we call linear and all-to-all. And if you actually solve the electrostatic problem, what you find is that the force that is exerted on every of those resonator will actually depend on the position of all the others, no matter the topology. So for these, even the position x1 will influence his position. And actually, the resulting force is an effective elastic coupling. Again, I won't get too long here because we'll get too much time, but the idea is that you can estimate those coupling terms, which will depend on the voltage drops, the capacity involved, and their susceptibilities. Using those type of coupling, we can finally build our network, which essentially, you just take multiple copies, so multiple copies of this equation. You plug those couplings. We also decided to consider some drives, and eventually you will solve this whole problem, which is a set of differential equation coupled. And in the right regime, meaning assuming small couplings and the fact that the frequency displacement is not too much when we are away from the limit cycle, but more importantly, the fact that all the frequency are almost all the same, so we have no synchronization problem. The final result is a nice equation like this one, which will describe every node in my network. And well, here I put the actual definition. As you may recognize, I decided to rename those as weights. Those are biases, because these will be the trainable parameter of our framework. On top of that, we actually also have the initial phases of the drives. And an important remark that I have to do is that the dynamics of this system is not like, as you may imagine, layered for a standard neural network. Those neurons are continuously interacting with each other. And on top of that, since this is a physical system, we may also have dependencies on the initial state of the system. So from here, we can finally start to describe the physical training loop, which is pretty standard, I would say. You take your network, you decide which are the input, hidden, and output nodes, and then eventually you start the loop. So you take your data set, you start the feed-forward propagation, meaning that you want to inject your inputs. This can be achieved through the input nodes using way stronger biases for the inputs not only. This actually kills their dynamic because essentially those two nodes will be locked on the input. And then eventually you just let your system evolve. So here comes the big advantage of using just dynamics for inference. And then eventually you record the outputs, you form the output vector, and eventually you compute your cost function. Of course, being a physical system, the hard problem is in extracting a physical gradient. But okay, I will tell you more in a minute. But the idea is that eventually, once you have the physical gradient, you just repeat until like converging the cost function to eventually zero. As I was saying, the physical gradient, well, this is one of the main problems for this type of implementation. And in my case, I have a sort of big problem that my dynamics is non-reciprocal, meaning I don't have a gradient descent dynamic. Now, I assisted many talks. Thanks. I assisted many talks this morning, so actually I have to look these again, but so far we couldn't really implement any of the protocol that we thought of. So actually the way we solved this problem was actually to use simulation. And essentially what we did was to create a differentiable model using JAX, which can be somewhat similar to a paper from Wright, in which they essentially use a physical aware training. And of course, this is a theoretical framework, so we cannot compute the cost function on the real implementation. So the idea was just to create a differentiable model. So using this whole machinery that I just described, what we've been able to do was actually to replicate the X0 gate, which is a very useful sanity check, let's say. So the idea is that compared to the AND and the OR, this is actually a nonlinear gate. It's simple because the dataset is really compact, just two inputs, two-dimensional, one output. And since we were using the phase, the encoding is just like this, meaning that the logical 0 is at minus pi half, and the logical 1 is at pi half. So we designed the network. It's a theoretical study. So we took 5 nodes. We initialized the parameters. And eventually, we defined a cost function which had to be 2 pi periodic to respect the 2 pi periodicity of phases. And then we used our digital training protocol. And we finally land on something like this, in which you can see the continuous response of the output node with respect to the input 1 and input 2. And you can see that at 0, 0, you get blue, which is again 0. At 0, 1, and 1, 0, you get red, which is 1. And at 1, 1, you actually get again 0. This is what was actually really nice, because it actually proved the expressibility of the network. But we were not quite satisfied, because especially in some points, you can have a bit flip as soon as you move slightly from the perfect input. The way we corrected it, again, in simulation, was just to enlarge the training region by adding some points around the exact input. And the final result is something like this, which was quite satisfying, especially when you think about putting noise eventually in the system. This kind of make it more robust. So conclusion as perspective, well, the main take-home message is that we eventually being able to prove the expressibility of the system. We actually estimated through this digital approach some real parameters that can be used in a true experimental implementation. And there are some perspective in the sense that we would like, first of all, to introduce noise in those equations to make the model more realistic. It would be nice, actually, if we can consider some bigger tasks, and so bigger networks and more complex tasks. And eventually, it would be nice if you can think of a different coupling so that we have a reciprocal dynamics, because that will make the training way more simple. So in the end, I would like to thank my 2 supervisors, Fabio in Loma, and Remy, who actually moved to Strasbourg, Florian, because he was very helpful, my team, and eventually the supporting. Thanks.
Thanks a lot for the great talk. Have you checked out my poster with Utrecht?
Yeah, I actually checked it.
After this shameless advert. You showed how, whatever the geometry, you get all-to-all coupling?
Yes, because essentially in any case, so the coupling is actually given by the fact that if one of the plates move, there is a charge migration on the rest, because there is charge conservation. And this will actually propagate even in the linear case, because you have a migration on the second, and eventually this causes a migration on the third.
So in practice, if you make a very large, long system, do your couplings still stay easy to tune?
These I don't know. I would say theoretically yes, because it's just a simple equation. Experimentally, I arguably say so. With arguably sustained, probably becomes way more difficult and eventually prone to noise problems. So yeah, not necessarily. Yes.
Okay, let's thank Andrea again.